Okay, let us look at the double integrals. Our interest in this section is in finding the volumes. We just have finished another section where we're finding the volumes. The solids that you have, which we are trying to find the volumes for, is not developed the same way. Okay, so previously, maybe if I can just bring in some geometry here. So this is the x-axis. So this is the y-axis. Say this is our region, right? So it's bounded by x is equal to 0 up to x is equal to some value somewhere here, right? And then some y values from y is equal to 0 up to y is equal to, say, f of x at the top there. So the solids that we were getting before, we were getting them by revolving this region around some axis, could be x, could be y. Then it will form some shape, for instance, which is like this one here, right? Which is like this one here. And then, right. So this is the kind of shapes that we are finding the volumes for previously. So for instance, for this geometry that you have here, so if you want to find a volume for this one, you may want to use the disk method. So what we have now under double integrals, we are bringing in a new variable. So we create a three-dimensional space instead of revolving this bounded region. We don't revolve it, but instead we have a z dimension which we have to consider now. Let me bring this region down here, right? So this is our region, for instance, along the x-axis. Okay, I have this line. Then from the y side, this is what we have. So our region is here. So now instead of rotating this around, we don't do that, but instead, let me just make a simple box. Now you see we have a new variable, right? So it's just a simple box here. Seems this dimension is large. Let me rewrite it nicely. I think it will be nice if it goes there. Like that. Like that. Okay, I think you can get the idea. It's just a nice simple box that we have here. Okay, so this is what we have now under three-dimensional space. And then how do you find the volume here? So the idea is the same as what we did here. No? We had to chop this into small pieces and try to find some very small volumes, and to improve that sum of those small volumes, we had to have a limit as the number of volumes tends to infinite, which then takes us to the integration. That concept is the same, also it also applies here. So what we can do is we can break this. I will not make very small rectangles because maybe it may not be clear. Let me just take a few like this. Just break it only a few times, otherwise my drawing will look so bad here. Okay, let me just break it a few times. Just a few times. And also we will not discuss all of it. Okay, so the concept is the same. Okay, so this is what we have. For instance, as you can see maybe here, along the x-axis, we have some delta x values, right? Along the y-axis, we have some delta y values, right? So this is what we have, Let me use a different color again to try to, otherwise it will just clutter and it will no longer be clear what is going on. So for instance, this could be delta x1, could be delta x2. I don't think there is enough space for this. Let me write it so here. So this is a delta x1, delta x2, delta x3, etc., etc. Say delta x4, right? Okay, so on this side, you can see on the y side, this could be delta y1, y2, y3. Okay, so the number of choppings is not the same, as you can see. It doesn't really necessarily mean they have to be the same, but I think what we have is that the way that we do it, we try to have these subdivisions along the y to be the same. In fact, I can even omit those indexes like 1, 2, 3 and just say delta y. Same thing also on the side of y. All of these ones are basically of the same width, okay? So basically the same length in terms of dimensions. So what are we doing here? So we try to create very, very small rectangles, so there must be a height as well, because we want to find some small volumes, because what we want to find at least an approximation of this V, and it will come from the sum of all of these V that are coming from these choppings. Maybe let us develop just this one here. Let me go back and use another color, for instance. Just develop this one. Right, hope you can see. That is the base. So what is the dimensions on the base there? It means the dimensions you can see is a delta x1, for instance, times delta y1. So therefore, we need the height, right? Because a box have 3 dimensions. Now the volume, we know it. So therefore, we need a height. How long is it when we go up? Because this is what we have, right? When you go up, so it is like this. So the height here, we can basically just take it from the center, maybe can do that from the center going up. So how long is this? You can see what is happening is that when this thing goes up, this length, it goes to this f of x y function. So corresponding to that position there, we can say 1, 1, right? So we can say f of x1, y1, right? So this gives us the volume of that small box there. So this we must say a plus another one. I don't think I will do all of them. Let me maybe just do this one here. I will not do all of them. Let me just pick any. Let me pick this one, right? So I can see also it goes up, it goes up. Say it goes up to here. It goes up to here. Okay, I'm trying to get a better shape. That is why I will not do all of them. You can see it takes time drawing these things. It takes time. Okay, I think you get the idea basically. And then again, what is the height from the bottom going up? then the height you can see it also goes into this f of x1, for instance. So now is x2. What is y there is also y2, right? So therefore it means the volume f of x2 y2, then the dimensions you can see is delta y2 delta x2. Okay, so the dimensions at the base at the bottom, so therefore is a delta x2 times delta y2. Right, so this will be plus, get the idea, up to some f of, there's not enough space, let me try to make some space on this side here. Right, just a bit, I'm trying to create space. Okay, yeah, so it's up to, say, f of x, say I, for instance, yj, let me do that, use i's and j's, and then it will be delta xi times delta yj, right? So there is of course a better way to write this. It means we're having I squared to 1 up to what? Maybe say up to n. You can see we have two summations here. There must be another summations. Say j is equal to 1 up to say m. So we are having f of x I yj, right, delta xi yj. Right, so as you remember this, I think I can just make it quick. You do remember even on the previous sections we've been talking about this, that to get a better value of this v, the number of these smaller v's, okay, these very, very small volumes that we are summing here must go to infinite. So we would like to have a limit as what? As n, as m tends to infinite, right? So that is what we want to see. So as n here is I is equal to 1 here, where we start, and the m here, j is equal to 1 from where we start, f of xi yj delta, right, delta x I yj. Now, what is the meaning of this tending to infinite? You remember even from the previous section. So we said once we have this statement where this limit it tends to infinite, then the rules allow us to replace this by integration. So replace this by integration. So each time we replace by the integral, right? And let us say maybe we were starting from a up to b along the x-axis. So it's a up to b. I'm just extend here, so I write a nicely away. Then also here, say this is d. We are moving from, let me just extend, hope you see it. I just want to write it away there so you see we have a c variable, right? So we are moving from c. Let me use a different color so maybe you can see it, because there's a lot of writing now. Okay, we're moving from c up to d, right, along the y-axis, moving from a up to, we're moving from a up to b along the x-axis. Okay, So therefore means we can have those limits in our values. So the x seems to be sitting inside here, so it means it comes first. So therefore what we do is, therefore the x limit must start, so up to b, then c up to d. So what are we having inside? So we are having this f of, remember the i's and the j's will fall off now when we put integration. So this is f of x, y, then the deltas again will be replaced by the d, so it's a dx dy here, right? So this is the volume that we get. Okay, so this will be the exact value of the volume below this f of x function, and then from the limit a up to b, and from c up to d, right? So this is the volume that we have. But the way we obtain this volume here, it's not a nice practical way that you can just apply everywhere, because the issue is that it takes time, as you can see. Yeah? It takes time to develop this. So there is another way of getting these volumes, which I also like us to discuss, because that is what is used in finding these volumes. Okay, let me bring in some geometry so that you can also have a look at it. And then this is what we'll be using right through, just as we start introducing it now. Okay. So what is this that we're having here? So this is this Fubin's theorem. Okay. So he gave us a practical way of, or maybe say an easier way of getting these volumes. Right? Let us say we're having our region. Let me bring it again. I think I've just made it so big now. Oh, maybe this naming is taking space. I don't have enough space so that I can write it on top here. Okay, so this is the x, sorry, this was y-axis. So this was y-axis, this was x-axis, then this is the z, right? And we were using just very, very simple geometry, where we just have constant values at the bottom. There is no function involved. Everything is just nicely straight lines. Again, this is not always the case. It's only because we just are starting now, so I just bring in a very simple shape. Okay. Hopefully it's clear. Ah, my geometry. Okay, my artwork is refusing to come together. I think you can get the idea. It's the same box as we had in the previous. How do we get then the volume using this Fubin's way of doing things? So basically what it says here, it says to get this volume V, which is the volume of this box, we fix one variable. I will say we fix this one here. So then we will get our delta x1, for instance, here. We will get a delta x2, for instance. I think you get the idea. up to maybe cell delta xn minus 1 up to the last one delta x n, right? So what do we have here? Standing on this side, we have the area, and the area is, remember, from single integrals. Think it will be when we start doing integration. You always learn how to find the area. So the area is simply just maybe say a to b f of x dx. We all remember this definite integral. So what this new way of doing things tells us is to that let us take this area and integrate it across the other dimension. Okay, so then it talks into this iterated way of performing these integrals. Okay, so we are having a multivariable function here, so it's the f of xi, then y like that. So what we have, we need an area on this side here. It will be c up to d, for instance, the dimension. So it means our integral will be c up to d, right? Then dy, so this area, you are happy with it, delta, right? Delta x I here, right? So these ones, we have to get as many as possible of these volumes, then we need to sum them, right? We need to sum them from I is equal to 1 up to I is what? Maybe say I is equal to n. Right, so we need to sum all of these small volumes. Then the way to improve this approximation is what? As always, is to have a limit as n tends to infinity. This summation here, I is equal to 1 up to n, c to d, xi, y, dy, delta, make some space here, xi. I think it's clear, and I think we're moving slowly enough with it. Okay, so as always, once you have the limits, as n tends to infinite, what happens? The rules allow us to replace this with the integral, so therefore all of this, replace it with the integral along the x-axis. Let us say we are from a up to b here, right? Say from a up to b. Let me use a different color for this. These limits, this one is a c up to d. I'm writing with the yellow over white. This one is a up to b, right? So therefore along the x-axis is a up to b. It's joining the previous integral which was here, which was c up to d. Then the f of x, I, now this just will be x, y, dy here, then dx, right? So what it therefore means, it means for us to get this volume, the simple thing that we just have to do is to perform integration with respect to y. When we do that, x is a constant in that way. Once we finish, then we perform integration again with respect to x now, and then we apply the limit of the x variable then this gives us the volume. So this is what the Fopin's theorem tells us. So in the same way that we have started with the integral with respect to y here, then we end with the x. The theorem tells us that you can start with any variable, so therefore v can still be obtained even when we start with the variable dx first, so we end with the dy, so therefore it means the a and a b will be here, the c and d will be outside. So it appears that we will get the same volume. So we just have to do this iterated way of finding the volume. So we perform the integration one at a time. So then we get the volume that we desire. So that is the idea basically here. Right. So what I will do next is that let us look at some examples and then try to perform this iterated way of integration and see what we get. So in my exercises, I'll just start with the simple exercises. I have them with me here. Then I will go to, I think it will be another recording. So I'll go to another recording and then I will also solve more. Okay, so let us start. Okay, so just look at the first exercise. Okay, I'll just read what the exercise says. Then I only will write what is important that we will be solving. So it says here, find the volume of the solid bounded above by the plane. Then they give us the plane. So the plane is x plus y is equal to 4 minus z. Then they say, and below by the rectangle, then they give us the rectangle R is equal to, right, 0 is less or equal to x, less or equal to 1, less than to 2. Right, so this is the question. So how do we find the solution? This one is really the simple case. So this one is the simple case. I will just draw the region for the sake of drawing it. When you have to draw the region, you don't have to worry about the y, sorry, about the z-axis. You can just focus on the x and y only. So let me do that. This is where you read your limits. So this is the x, so this is the y. So what we see is that it really clear, it's obvious, it's simple. It's just from 0 to 2. So therefore this is our region here. And then it's from 0 to 1. Say from 0 to 1. So this is what we have. Right? So this is what we have. So we are integrating this v over this just constant limit. So let us start with x first, then we'll end with the y, and y is 0 to 2, x is a 0 to 1. So we need to have a z of xy here. So we will get it from this equation from the top there. So we make z subject of the equations there. So it therefore means z is equal to 4 minus x minus y. So we're starting with the x, we end with y. Oh, this is very important that the limits that you have here, they always match the variable that you have inside. So do also the limits that you have outside here, they also match the variable that we have outside. So basically, if we have this dy outside, therefore the y limits must be on the outer integral. So too, if the dx is inside, therefore the limits along the x-axis, they must come first. Right, so let us try to solve this one then and see what we get. Okay, 0 to 2. We don't have any business with this for now, so we can just put it outside. So the way we perform the integration is the same way as what you will do for the partial differentiation. So when you are still working with this other variable, you keep the other one a constant, you don't do anything with it, then you focus on one until you finish, then you go and concentrate on the other variable. For instance, we have a dx, so let us apply the dx for now, so it means y is a constant, so therefore this term will give us a 4x minus, therefore integral of x power 2 over 2, just the same properties of integration they apply. The only thing is that now there's a new variable, and then there is that concept of partial differentiation, one variable at a time, so therefore it's a minus. Y is a constant, therefore, because we have no interest on it for now, so this will just be a y. Therefore, with the x, we apply the limits 0 to 1, then it's a dy, right? So 0 to 2. Then let us see what we get from inside here. So we are getting a 4 minus 1 over 2 minus y. Then we have to apply the lower limit, but we can see the lower limit will don't give us anything. So I'll just close. Let me simplify this a bit, or maybe just say put this number together. You can see this is a 7 over 2 minus y. Instead of going down, let me just say and continue here. So now we have to integrate with respect to y. So this we can see 7 over 2 minus, therefore y squared over 2, the limits. Then we apply our limits here. You can see means we're having a 7, then a 2 times over 2 minus 4 over 2 minus the lower limit will be 0, just to be 0 there. So we are getting a 5. So 5 unit cubes here, right? So this is what we are getting for this first exercise. So let us look at another one and see what we get. So they say evaluate the integral. Let me erase to make a space. Right? Okay, so number 2. So they say evaluate the integral, and then they give us, so it's a 0 to 1. It's a 0 to x squared. So it's a sine pi x squared all over x dy. So it means we must integrate with respect to y first, dx later on. Okay. So how do we do this one? So the order that you integrate with, starting with x or y, it's very helpful, because sometimes for some integrals we are not able to integrate if you started with the wrong uh, variable, so maybe you get stuck. So you just need to be careful with that. So if you see that things are complicated, maybe starting with the y, then you must change and start with the x. But of course, when you do that change, then you must also take note that there must be changes on the settings of your limit. Okay, so you must do something with the limit as well when you change order. Okay, so what do we get from here? So this is equal to, so 0 to 1. So we integrate with respect to y. There is no y inside, it means that whole integrand here is just a constant. So therefore, let me just rewrite it. So therefore, we are having a sign. So it's a pi x squared over x. Therefore, y from 0 to x squared. Then we still have to integrate with respect to x. As you can see, when we apply this limit, the variable we get, it work nicely with the next with respect to variable. So this also tells you that you are on a good track, because if this was the x, then you must put a y, but you have a dx standing outside here. Something is not right. Another thing also to mention is that in these two integral signs that we have here, the limits which have a variable, for instance like these ones, must always be on the inner integral, not on the outer integral. So the outer integral is always having just constant limits. Okay, so the outer integral is always having constant variables. Okay, so therefore we have a 0 to 1. So I can see we will get the x squared there. So it will be x squared over x. Okay, maybe let me just delay a bit. So it's a pi x squared over x. So apply the limits. Upper limit is x squared minus lower limit, which is a 0. So I'll just omit. I will not write it. Then with the dx here. So we have a 0 to 1. So x squared over x, you can see it's a x. It's a sine pi x squared dx. So now we have to integrate this. You can see it's a nice, easy u substitution problem. Let me apply the u substitution. So then I will say let u is equal to pi x squared, which therefore means our du is equal to 2 pi x dx. So therefore means, as you can see here, we make some space. It therefore means x dx is equal to 1 over 2 pi du. Right. So therefore, as we continue, it's a 0 to 1. So the x dx is all equal to this right hand side here. Right. So let me just write the sine function. Therefore, it's a u here. So it's a times 1 over 2 pi du. Right. So this is equal to 1 over 2 pi 0 to 1 sine u du. Right. Okay, so therefore means we have 1 over 2 pi. So the integral of a sine, it's a cos function. It's a cos u. Our u, remember, is a pi x squared. You have to apply the limits. But this is a negative. Okay, so it's a minus cos function. So then we have a minus 1 over 2 pi. So it means we have a cos pi here minus cos 0, right? So this is equal to minus 1 over 2 pi. So what are we getting here? We are getting a minus 2 from inside here. So therefore the final answer is 1 over pi. So 1 over pi unit cube here for the volume. Right. Okay. You can see we're having some nice simple problems. So we just are discussing only the operation. So hopefully it's clear, you are getting it. Okay, so this will be the third one. So then the next one, what I will do is I will try to look at changing the order. Let us do this one last one. Then we'll shift to something else. Zero to y squared. It's 1 plus y cube dx dy, right? Okay, so how do we integrate it? I think as we can see also, it's 0 to 1. So this whole integrand here seems to be just be a constant because our interest is still with respect to x. So therefore, let me just rewrite it. 1 plus y cube. So the x is the integral from 0 to y squared dy. So therefore, we are getting 0 to 1. Let me write the y squared here. Upper limit 1 plus y cube. The lower limit will be a 0, so I omitted that one. So this is equal to, you can see here we can also use the u substitution, or you can use compensation method, is up to you. I'll use the u substitution myself, but compensation is easy and fast. Okay, so we can let u is equal to 1 plus y cube du is equal to 3 y squared dx. So it therefore means y squared is equal to 1 over 3 du here. So therefore when we continue, we have 1 over 3 outside, which is a constant, 0 to 1. So therefore it's a u raised to 1 over 2 du. So this is equal to 1 over 3. Remember, u is equal to 1 plus y cube. Then the integration will give us 3 over 2 divided by, so I'll say times 2 over 3. Then from 0 to 1, right? Then when we end this here, what are we getting? Okay, so when we end this, we're getting a 2 over 9. Then we apply the limits. 1 cube, so this is just a 2 raised to 3 over 2 minus 1 and a 0. It's a unit, 3 over 2. So therefore we are getting a 2 over 9. Then it's a 2, 3 over 2 minus 1. I'll stop here. Right, so so this is how we perform doubly integration. Okay, so this is how we get to the solutions. So the next thing that I want us to look at is the case where you have to change the order of integration. Okay. But again, I don't want this recording to be so long, so let me see how long this one is. I think it's still below an hour. Okay. Yeah. So let me continue with this one. Mostly if the recording becomes so long, so what I will do is that I will stop it and continue on another video. Okay, so let us reverse the order here. I'll say reverse the order of integration. Okay, so this is what we want to do. Let us use some examples just to show how do you reverse the order of integration. I have two examples which I want us to go through. Okay. The statement says determine the integral by reversing the order of integration. Then they write the problem for us. So this is the first of these two that I want to solve. So they give it like this. It says 0 to square root 2. It says 0 to 2 minus x squared. It's ax a raised to x squared dy over dx. Okay, so there we have it. Now, how do we reverse the order? Okay, so we have to focus on these limits. So let us write a region. These limits, as they are here, they are coming from a region. And the region is always on the x and y axis. You just forget about the z direction when we are trying to develop the region where we will have to get the limits from. So you focus only on the xy plane. So as you can see, so the outer limit here, which is the limit of the x, it says it's from 0 up to some square root 2. Say square root 2 is somewhere here. And then the limit, this inner limits, these are the values of y. And it says y is from 0 up to some function. So what is the graph of this function? When x is equal to 0, we see that y is 2. When x is 1, somewhere here, when x is 1, y also is 1, so it's dropping, is coming like this. In fact, when x is the square root 2, this is where y passes, so the curve goes like this. So I'll not bother with what is happening on this other side. Even on this other side below, y is equal to 0. Remember, y is equal to 0 is here, then we go up. So anything here on the negative side, I will not bother myself with. So let me just cut here. Right, so square root 2. Okay, so now we want to find y value will be outside now. So this is up to 2. So therefore, since the outer limit is the one that is carrying the constant, so therefore what we see from here that y is from 0 up to 2. Y is equal to 2, right? The x on the other side, x is from 0 up to the curve, right? 0 up to the curve. So what is this curve? So this is y is equal to 2 minus x squared, which was the upper limit when you go up. Now we're going this way, so we need to have this, but now as x in terms of y, so it means we're having y minus 2 minus x squared. So therefore means x squared is equal to 2 minus y. Therefore x is equal to plus or minus square root 2 minus y. Okay, so of course you can see the minus is this side, so we need the plus side, which is this side. So therefore we are taking 2 minus y from 0. Right. Okay, so then our z function, so we continue with it. So it's still the x, a raised to x squared, but now this is dx dy now. Okay, so this is the new integral that we have to solve. As we can see now, it becomes so easy to work with this integrand. We can just use the u substitution, then we get the answer. Okay, so let us do that. Okay, so let u is equal to x squared, du is equal to 2x dx. You can see x dx is equal to 1 over 2 du, right? So therefore this is equal to 1 over 2 is a constant, so 0 to 2. Then we're having 0 to square root 2 minus y e raised to u, right? Du dy, which we're not doing anything with it at the moment. So this is equal to 1 over 2, 0 to 2. Then the integral here is e raised to u, but remember u is x squared. So we just bring it back, then we apply our limits up to square root 2 minus y, then a dy. Right. So let us apply the limits. It's 1 over 2, 0 to 2. Try to apply the limit here. So the power 2 will remove the square root, so we'll be left with a 2 minus y minus e raised to 0, that is a unit, dy. So therefore this is equal to 1 over 2 now. Then we have to integrate now with respect to y. I think that one is a simple integral. You can see this will be e raised to 2 minus y. The derivative of this power here, it's a minus 1, so therefore this will have a minus. So it's a minus y here. Okay, apply the limits. The limits is 0 up to 2. Right? I think you can see we are done. So this is equal to, minus seem to be common. We put it outside, minus 1 over 2. So therefore, we apply the limits. So it will be e raised to 2 minus 2. Okay, I'll just write it as 0 minus. Okay, it's a plus now because the minus is outside. So it's a plus 2 here minus lower limits. So it's a e raised to 2 minus 0. So therefore raised to 2 plus. Okay, it's just a 0. Okay. So therefore this is equal to. So it's a minus 1 over 2. So therefore I have a 3 here minus e raised to 2. Let me erase and allow the minus to be absorbed and go inside. So this is e raised to 2 minus 3. I'll stop here. Right. So this is what we get. So the aim was in discussing how do we change the limits. So let us bring in another one. I think this will be the last one on how to change the limits. Okay. Just do this number 2. Okay, so I have it here. So it says evaluate the integral by reversing the order of integration. Okay, then they give us as a 0 to 1, as a 1, as a y to 1. Then it is the square roots 1 minus x squared dx dy. Okay, they give us like that. We have to reverse the order. So let's try to bring in some geometry here. You never have to bother yourself with the z again. Place only just x in y plane. X comes first, yeah? So therefore this is the x values. So it means x is equal to y. So it means there's a line like this. X is equal to y. So x is from this line up to the upper limit for the x is 1. X is equal to 1. Okay. So the upper limit for x is equal to 1. Right? So x goes this way from here straight. So this is the upper limit. Right? Okay, so this is the upper limit. Then what is the y? So y of the constant is from 0 up to y is equal to 1. Right? So therefore we can now have our limits. Now x will be outside, so x now will take the constant from 0 to 1, this line here. So therefore means x now must take the constant is 0 to 1. Now y must be the one that is taking care of the variables, this function here, because it is the inner limits now. So we're still having our z, which is 1 minus the x squared, no problem, but y comes first, x comes last. So what we say now is that y will be from 0, it must be up to the function now. So therefore y is from 0 up to y is equal to x. Right. Okay, then we perform the integration. So the integration here, so therefore 0 to 1 outside. So the integration, there's no y here, so therefore it means all of this is a constant. So therefore over square root 1 minus x squared from 0 to x, right? So therefore means we're having 0 to 1 x, this limit 1 minus x squared. The lower limit is a 0, and then it will give us a 0 basically. So I will omit it. Then we're having a dx. So we can use a substitution, a compensation method here. But we see that the derivative inside is inside of the square root. Inside of the square root here, the derivative is minus 2x. We do have x outside, but we need the minus 2, so therefore we'll balance with minus 1 over 2. Then 1 minus x squared. Therefore, 1 over 2 plus 1, so it's a 3 over 2 times 2 over 3, then the limits. So, so 2 and 2 will cancel, can see. So then we are left with minus 1 over 3. So it means we're having a 1 minus, upper limit is 1 as well, okay, so it's 3 over 2 minus 1 and a 0, 3 over 2. Therefore we are having minus 1 over 3, 0 minus, so it therefore means we're having 1 over 3. That's the answer. Okay, so this is what we have. So I think this will be enough to discuss how you change the order of integration. Now what I will do is let us bring in this other way also, which help us make the integral easy. Okay, and what is that? Is the polar coordinates. Polar coordinates. Okay, so let us try to find the double integral under polar coordinates. Okay, what I will do is I will try to discuss this using examples so that we learn how to solve it. But of course, we need to be able to move from this other form, which is rectangular form, to this polar form for us to be able to solve these problems. Let me bring in this small table here. Say this is rectangular form, rectangular coordinate, right? Draw a line or separate. I will extend the line as we go down. Then I'll say this is polar coordinates. Okay, so the first thing that I want us to look at is number 1, how do you go to a point in polar coordinates and in rectangular form? Okay, so this will be the x-axis, this will be the y-axis. So say we have a point in space, just any point P. So with the rectangular coordinate, to go there to this point, you need to know your x value. You also need to know your y value. So a point here will be x and a y values, okay? So this is what you need. In polar coordinate, this will be the x. So basically the polar coordinates sit on top of the rectangular system. To go to any point in space P, you need two things. You need the radius, then you need the angle. So the point will be the radius and the angle. So that's what is needed. Okay? So if we are shifting from this side, and then you want to write things in polar form, so what do you do? Okay? You can actually get the equations that will help you to shift. So the x here is defined in terms of r and a theta. Y here is in terms of r and a sine theta. So what you can say that r, which is this value, r will be r squared. So it will be r squared is equal to x squared plus y squared. Okay? You can say obviously that is coming from, for instance, the x there is coming from the fact that cos theta is equal to x over r. So if we make x subject of the equation, therefore we see what you get. Also the y is coming from sine theta is equal to opposite over hypotenuse. Opposite is y. Opposite over hypotenuse. So of course we can say, making y subject of the equation, you get this y is equal to r sine theta. Right. So two, what I also would like to bring in before we go to problems, let me extend the table. Try to get a better line here. So this is number 2. Okay, so the subdivisions. Okay. This is the x-axis. This is the y-axis. When we are chopping this region here, trying to get these rectangles, which we further get these small pieces of these volumes, this will be having a delta x here. This will be a delta y, right? So therefore this, it makes this small area here, delta a here, to be delta x, delta y. Let me rewrite it. So it makes this small area, delta a, to be equal to delta x times the delta y, which this further develop into this dx is equal to this dA. Let me write it at the bottom here. So this, now when you are in the integrals, now trying to find these deltas to infinites, going to the integral, this develop into this dA, which is equal to dx dy, which according to Fubini's theorem, this same dA is also equal to dy dx. Okay, right? So this is what we know. So therefore what we have is that the volume here, v, is equal to, then we can have the limits, which I can say x1 to x2, y1 to y2, then this f of x1, so therefore it's a dy dx. Then according to the theorem we are using, we can also have the case where the limits are changed and we get the same value. Okay, v also is still the same. Okay, trying to make space. Okay, so v can still get the same value even if the limits are twisted. Okay, so f of x, y, dx, dy. Right, so this is what we have on the rectangular side. Then on the other side here, on the polar form, right, the x-axis, the y-axis. On the polar form, we are always standing in the origin, whether we are determining the radius or we are determining the angle. It's always irrespective, even if maybe our origin is only, maybe it's just here, it doesn't come and maybe pass, like maybe if it's a cycle like this, again, even if it's just here like this, but we are always standing here and you look what is happening far away there. Okay, so we are here, say we have this, then we have this. We want to determine this delta A, this area for the polar form is equal to what? Okay, so of course we expect that difference, right? So this is along the radial direction, as you can see. So therefore we have a small delta r here, and again this is along the angle direction, so then we have this delta theta. Okay, but what we have here, we need to know the radius r. Where is this dA occurring, this delta A, where is it occurring? So therefore what we say that when we develop this into this integral now, this it becomes r dr d theta. It never changes. Okay, so unlike the rectangular form where you can start with any variable, for the polar form it's always r first, theta is always a constant. So therefore for the polar form v is equal to theta is always outside, as theta 1, theta 2, then r1 could be r of theta, could be r of theta. This could be a function in terms of theta, this one. Then the function here is therefore r theta. Then you can say therefore dA, our dA is r dr d theta. Okay, it doesn't change. Right, so this is what we have. So let us look at some exercises which require us to use the polar coordinates. Okay, I do have some here. Just try to go through them. So I'll go up and erase to make some space. Okay, let me try to erase Let me remove even the title, polar coordinates. I have to make some space. Right. Okay, so this will be number 1. They say to us, determine the integral using polar coordinates. Then they give us, then there's a d here, so it's ax, then it's x, y squared, so it's ax y squared, dx, dy. Then they say where d is equal to, so it's ax, y, so it's x squared, y squared, less or equal to 4, says x is greater or equal to 0, y is greater or equal to 0. Okay, right. So this is the problem that we have to solve, and they tell us we must solve it in polar form. So we must change from this rectangular system into polar system. So the polar form, what it helps us when we have to solve problems which are having circular structures. Okay, so the polar form work very well with the circular structures. And maybe you can see, for instance, we have a cycle here. So the polar form is very happy with these structures. So it's able to make a complicated integral becomes very simple when you change it to polar coordinates. Okay, let's look at the region so that we can see what will be our limit in polar coordinates. So let's try to put the region down into this diagram here. So it's x squared plus y squared less or equal to 4. It means the r is equal to 2 there, because we can see this is a cycle. This is a cycle of radius 2. Right? Let me draw it. Cycle of radius 2, but I don't have interest on the other side because you can see these other statements. They tell us that x is greater or equal to 0. So it means there is no interest on this side. And it also says y is greater or equal to 0. Y is negative below here, going down. So it means our interest is from 0 going up with the y-axis. Okay. So therefore our region is basically like this. And the radius is 2. Means x also this side is 2. Right. So let us come therefore and solve. Theta is always outside. You can see theta means it's from 0 up to pi over 2. Always theta, you read it standing in the origin from the x-axis going up. Always like that. Irrespective of your region where it is, you always must be here where you touch it, where you the last time you touch it. Okay, so that's how you read the theta. Then the radius is 0 to 2. So this is a simple case. Radius is a constant as well. Then x, you know x is a r cos theta sine. It means it will be r squared sine squared theta. Dx dy, there is dA, and our dA in polar form is r. Dr d theta. So therefore this is equal to, so 0 to pi over 2, 0 to 2 here. It means we have r raised to 1 raised to 2, so this is r raised to 4 cos theta sine squared theta dr d theta here. Okay, so then we integrate with respect to r first. Pi over 2. It means we're having r raised to 5 all over 5. We have to apply the limits here, 0 to 2. Let me just write these other values here. And start with these ones. Then r raised to 5 all over 5, 0 to 2 d theta. Okay. Sorry. This is equal sign 0 to pi over 2. So therefore we have a 2 raised to 5 there. 2 raised to 5 is a 32, so I may write 32 over 5. 32 over 5 cos theta sine squared theta d theta here. Right. So now we have to integrate with respect to theta. Let's see what you get when you do that. So 32 over 5 is a constant. So we can use substitution. Just do that, it will be quick. So we're having a sine squared, but the derivative of a sine is a cos. And it's just a cos without any, say, minus sign. So therefore what we will get here, we will get that the integral here is in fact a sine cube theta 1 over 3 0 to pi over 2. 32 over 5. Therefore we can apply the limits. Let me allow the 3 to come outside, it will be common. Therefore this will be sine raised to 3 pi over 2 minus 0. What are we getting from inside here? We get sine pi over 2 is a unit. So therefore we just are getting 32 over 15. Right. Okay, let's do another one. So this will be the last one. Okay, let me go up and erase. Okay. Okay. So they say determine the integral using polar coordinates. Then they give us the integral. So minus 1 to 1. minus square root 1 minus y squared to 0. It's a cos x squared y squared dx dy. Okay, so there we have it. So they want us to use the polar coordinates. Just try to draw the region again to see our limits in polar form. So this integral is having the x limits from the lower limits to the upper limits. So therefore means this lower limit, this is x, is equal to minus square root 1 minus y squared. Okay, I think you can see where this is coming from. So basically what we have here is that if you will have a minus equal to the square root, I think you can see though where it's coming from. Power 2, you're having x squared 1 minus y squared. Therefore you can see this is a cycle x squared y squared is equal to 1. So this is a cycle of radius 1. So this minus square root is coming right from here, because it means you can have x squared is equal to 1 minus y squared. Therefore x is equal to plus or minus 1 minus y squared. So on this cycle, you know the plus side is this side, because it's on the plus side, is on the plus side of the x-axis. Then this side is on the minus side of the x-axis. Right, so this is what we have. So therefore, let me extend this here. Therefore the lower limit is a minus, right, is from there up to x is equal to 0. Then the y limit is from minus 1 up to 1. Okay, this is just the radius value. Okay, let us come back and try to solve now. Is therefore mean in polar form. So in polar form, theta is always on the outer integral. In order to say that moving from here, where theta is 0, we start to say the region when theta is pi over 2 up to the last time when theta is 3 over 2 pi. Okay, again we always start counting from this line. Okay, along the x-axis is a 0 going up. You don't say, oh, because you first see the region here, therefore this is 0 up to. You always start from here, then you go this way, irrespective of where the region is. Okay, okay, so therefore having pi over 2, so it means the region is from pi over 2 up to the last time where we see the region is when we're having 3 over 2 pi. So the radius is simply just 0 up to 1. So it's a cos x squared plus y squared. We know this is r squared dx dy. This is r dr d theta. Right, so now we have to integrate this, see what we get. So it says 0, sorry. So it's from pi over 2, 3 over 2 pi. We have a r squared inside and the r outside. We can use u substitution there, where we'll have let u is equal to r squared. This will mean du is equal to 2 r dr. Therefore, we can say r dr is equal to 1 over 2 du. Right. So therefore, we're having 1 over 2 as a constant of the integral 0 to 1 cos u here. Therefore, du d theta. So this is equal to, let me erase, 1 over 2 pi over 2, 3 over 2 pi. So derivative of a sine is a cos, so therefore cos will go back to the sine, so therefore this will be a sine. Remember, u is a r squared. Then we apply the limits, which is a 0 to 1 d theta constant. So what are we having here? Sorry. So it's a pi over 2, 3 over 2 pi. So it's a sine 1 minus sine 0. Sine 0 is 0, so I will omit it. D theta here. So therefore we are having 1 over 2 sine 1 is just a constant. Then the integral from pi over 2, 3 over 2 pi. Right, so we are almost there, finishing now. So it's 1. Then we apply the limits here. So it's a 3 over 2 pi minus pi over 2. What are we getting from here? So it's a 3 over 2 minus half. So 2 is common. 3. It's a 2. So this is a 1 over 2 pi. Okay. I think that will be it. I'll stop here.